Ladies and gentlemen, good evening. On behalf of IEEE ADSF SIGHT, it's my privilege to extend a warm welcome to each and every one of you to our weekly interaction program. As we gather here today for the fourth interaction program, we embark on a journey of exploration and discovery into the realm of sustainable energy. I also extend a warm welcome to our chief guest, Engineer Sivaraman P, Senior Member of IEEE, to give a technical talk on utility scale solar PV system. I now invite my friend Hashni to give a brief introduction about the chief guest. Thank you.
Good evening, everyone. It is my honor to introduce our esteemed chief guest, Sivaraman P, a young and dynamic engineer. Sivaraman possesses a wealth of expertise in power systems, with a particular focus on renewable energy integration, grid impact analysis for EV charging infrastructure, and power quality analysis. Not only is Sivaraman a senior member of the IEEE and a member of the Institute of Engineers, but he also holds the prestigious professional engineer certification. His role as an ambassador for IEEE initiatives, including smart cities and previous YP powering the future, reflects his dedication, fostering collaboration and knowledge exchange within the industry. Please join me in welcoming Sivaraman, whose expertise and leadership continue to inspire and shape the future of power systems and renewable energy. Welcome, sir.
Yeah, thank you. Can anyone confirm whether my voice is audible?
Yes, sir. Voice audible.
Yeah, okay, good, fine. Thank you for Harshni for your introduction. So once again, I am welcoming you to the fourth interaction section of IEEE ADSF SIGHT on solar energy. So today I will cover about the ground-mounted solar PV system. I'm sharing my screen. Let me know whether my screen is visible to you. Can anyone confirm whether my screen is visible to you? Vinay sir, can you confirm
Yes,
whether
sir.
my screen is
Yes,
visible to you?
your screen
Yeah.
is visible.
Your screen is visible, sir.
Yeah, good, fine. So I will directly go through this today presentation. So in the last session, we seen about the rooftop solar PV system. Sorry, the design of rooftop solar PV system using the string inverter. So in this session, I will explain about the ground mounted solar PV system. So this ground mounted solar PV system mostly in simple words, installing the solar PV modules on the ground. So in simple words, that is ground mounted solar PV system. So as you seen in this figure, so all the solar PV modules installed on the ground. So some of the so here you can able to see. So these are all our solar PV modules. Solar PV modules installed on the model mounting structure MMS. So these kind of systems are called as ground mounted solar PV system, and these ground mounted solar PV systems are mostly used for utility scale applications. So where the generated energy will be exported to the grid. So most of the large scale power plants, mostly in megawatt range, starting from 1 megawatt to even gigawatt range. So those are all mostly comes under this ground mounted solar PV system. So in this system, mostly we will use the central inverters. So on the day earlier, I explained about what are the different types of inverters available for solar PV applications. As an recall, I will once again reiterate. So it is string inverter, central inverter, and micro inverter. So most of the ground mounted PV applications, string inverters are widely used, and it will have an substation. So in I have not explained anything about substation till now, because rooftop based applications, substations will not be required or will not be in place. On the same time, for the ground mounted PV applications, most of the installations, the ground mounted solar PV system required in substation. On the same time, high voltage and extra high voltage transmission line to interconnect the solar PV system to the existing power grid. So it will be in high voltage level up to 110 kV or 132 kV, and the extra high voltage starting from 220 or 230 kV level to 400 kV voltage level, right? So this is the general about the ground mounted solar PV system. Coming to the layout. So in this slide, what you are seeing is the typical layout of the ground mounted solar PV system. So here the boundary is marked, right? So this boundary is the total planning area. So this is the total planning area. So here these are all water reservoirs, or some rivers or lakes, something. Okay. So here challenges will come in an area. So here we have to select the area which is available for the module mounting. So one thing we want to ensure that it should not comes under the water reservoir or any lakes or rivers. Okay. So these are all the areas will be affected by the waters, or waters is logging, or water will get affected. So if we are installing the module on the water reservoir or river, what will happen? Suppose if water is not there, there will be no problem. Suppose suddenly some flood came, then entire infrastructure will be affected. Sometime we can't imagine. So those infrastructure will be destroyed by the flow of water, right? So we have to taken care. We have to take care of that aspect. So in project, some location also in between water reservoir will come. So so we have to take care of that aspects. Okay. So these aspects will be mostly taken care by civil engineers. So they will perform the land survey or land analysis. Based on that, they will try to identify what are the areas we can able to install the solar PV modules. Okay. So here some of the things I would like to highlight. So here in this area, some lines are there, right? Some shadow is there, right? So these shadows are solar PV modules where we are going to install the solar PV modules. This is that area. The light brown color is the module installing area. So this will be an inverter room 1. This is inverter room, short form IR1. So in the inverter room, I will explore in the inverter room where we are going to have the inverter, then inverter duty transformer, switch gears, including low voltage switch gear, high voltage switch gear, and auxiliary equipments. Those things will be there in this inverter room. So similar to that, there are in this layout, there are 4 inverter rooms are there. So for easy understanding, the similar colors are one inverter room. So here it is pink color, right? So all the pink colors are one inverter room. Let's say inverter room 2. This color will be inverter room 3. Then green color will be inverter room 4. Substation will be placed at this location. Yes, substation. So from here, the power will be exported to the grid through the transmission line. So this is the general overview. So from this inverter room to this substation, we can export the power through the cable. This we can be through cable or transmission line. In simple words, the overhead line what we are seeing in the road, right? So similar transmission line we can use for exporting the power from one location to another location. Okay, so moving further, this is the typical single line diagram of an ground mounted solar PV system. I know this figure is not clear, but I will have some quality figures in the upcoming one. Okay. So these are all the inverters. This is the inverters. Uh, this is the inverter duty transformer. This is transformer. Then this will be the switch gear, medium voltage switch gear, 33 kV or 22 kV or whatever. Then this is the cable, 33 kV cable or transmission line. Okay, so this is the main switch gear at the substation, 33 kV switch gear at the substation. Then this is the outgoing feeder to the transformer. This is the power transformer to 20 kV bar 33 kV. So based on the power rating, the transformer rating will be there, right? So this is the clear view of it. So here you can able to see. So this is the inverter tutory transformer. Its primary voltage is this side is 33 kV, and its inverter side it is 630 volt. So most of the central inverters are available in the voltage level of 590 volt to 690 volt, or sometime even 700 710 volt also will be available. So that is based on the power rating and the inverter manufacturer. So this is a 5 winding transformer. One primary winding will be there and 4 number of secondary winding will be there. That is LV winding. So each LV winding will be connected to the individual inverter like this. So this is the inverter 1 and this is the inverter 4. 2 and this is the 213. Okay, so all the DC solar PV panels in the series parallel combination after the stringing etc will come to the inverter. So similar to that, this will be connected to the another set of DC panel. This will be the another set of DC panel. Okay, then finally the transformer primary winding will be connected to the medium voltage switchgear in the substation. Okay, so in this example, what you are seeing, it is 12.5 MVA. So this transformer primary winding is 12.5 MVA. So each LV winding is 3.125, 3.125 MVA. MVA. So each winding is 1.25 MVA. So each inverter is rated for 3.125 MVA or 3.125 kilowatt. Okay, so the combined capacity is 12.5 MVA. So the transformer impedance is 7%. It is ON, AN, oil natural, air natural. So the vector group is there. In the high voltage side, it is star. In the low voltage side, it is delta. D11, 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 D11. Okay, so it having the OCTC. It's not having the OLTC. It will have the OCTC, off circuit tape changer on it. Okay, then here the medium voltage cable will come connecting the transformer to this inverter room switch gear. So entire this part will be in one inverter room. In this layout I mentioned here, right? Inverter one, room one. So in that room, these inverters inverter duty transformer switch gears will be placed. Okay, so this outgoing will be mostly with cable or sometime transmission line as well. Okay, so this will go to the switch gear. So in this slide, what you are seeing is an 33 kV switch gear panel in the substation. So it will have the multiple incoming supply from the solar PV area. This is the 1, 2, 3, 4, 5. Okay, so this panel having 5 incoming supply from the inverter room like this, and it will it having one output, actually one output to the power transformer. This will go to the power transformer okay. So here you can able to see it is 33 kV 630 ampere VCB vacuum circuit breaker. It has the access capacity of 25 kiloampere for 1 second. So this is the bus bar rating, 2500 ampere aluminum bus bar. So this is the PT which is used for instrumentation purpose. These are all the CTs. This is the CT for monitoring purpose. This is the CT for the protection purpose. Okay, so similarly on the outgoing side, again it will have an PT. Some projects PT will be there additionally. So this is the CT for the protection and metering purpose. Okay, so the PT is connected to the common bus is called bus PT. PT means potential transformer. So suppose the PT is connected to the individual line, whether it is to the transformer line or whether it is the outgoing line to the solar plant, that this PT is called as line PT. Okay. So moving further, this is the transformer. This is the power transformer of 100 MVA. So it's having the power rating of 100 MVA. It is ON, AN, ON, AN, AF type. So we can use this transformer as an ON, AN, oil natural, air natural, as well as oil natural, air forced. So it having the vector group of YN, YN. So both side is star. So that is YN, YN. Start grounded, star grounded. So this transform or the outgoing feeder of the switch gear to the transformer, 33 kV medium voltage cable used to connect. Okay, so this will be inside the substation yard area. This will be most of the cases. These switch gears will be mostly in indoor mostly. Some location it can be in outdoor also. So both indoor and outdoor, there are some additional requirements or some different requirements will be there. Okay, so from this 230 kV side, this will be an 230 kV voltage level. So from here, there will be an transmission line that will connected to the existing substation. Okay, so this is a simplified single line diagram. So this diagram is more clear. So this is an solar inverter. This is an solar PV module. So solar PV module is connected to the inverter. This is a transformer, inverter duty transformer. Then this is the medium voltage. It can be a 22 kV or 11 kV or 33 kV. 33 kV. So this line normally called as collector network. So this kind of medium voltage lines are called as collector network of the solar PV plant. So this will be get interconnected with the grid. Okay. Suppose if you have the grid at this location, that grid voltage is 33 kV. So our plant voltage is 33 kV. So in this case, we no need a power transformer. We can directly connect 33 kV our plant. This will be in the plant. This side is the plant. In the upside, it is the grid. This side is our plant. So in this case, we no need to have a transformer here. We can directly connect this 33 kV voltage level into the existing grid 33 kV voltage. Suppose the existing network is 132 kV. Let's say 132 kV. So in that case, what we have to do, we shall have a power transformer which is rated of 132 kV bar 33 kV. So 133 kV side will be connected to the existing grid and 33 kV will be connected to our plant. Okay, so like this, the solar PV system in a broader perspective is look like. Okay, so in a solar ground mounted solar PV system, large scale, more than 50 or 60 megawatt, mostly it will be get connected to the high voltage and extra high voltage. In those locations, we need a power transformer, this one. So the where the installed capacity is less than 50 megawatt, and in the very nearby there is an medium voltage line up to 33 kV. In those locations, power transformer is not required. We can connect the existing grid to our power plant with that voltage level itself. Okay. So I hope everyone is clear. If you have any doubt, you can unmute yourself and you can ask the question. There is no doubt. Moving further, this is the solar PV panel installed on the ground. As I told, these are all the plan. I hope you may remember what I told in the first session. In a ground-mounted solar PV system, it will be the modules will be installed in a large area. If you go inside the solar PV module, if you just rotate across the 360 degrees, all the direction you can able to find the solar PV modules only. So because for getting the higher power, we have to install the more number of PV modules, right? So this is this photograph of, were taken in such large scale utility power plant only. So this is the solar PV panel. So where the panel is installed, that structure is called as module mounting structure. So I told in the first session, based on the number of panels installed, we can say this structure in a P. This is 1, 2, 3, 4. So okay, so totally 4 rows the panels are installed. So this is called as 4P structure. This structure is called as 4P structure. Okay, suppose if only 2 panels are there in this one module mounting structure, then it means it is 2P structure. Okay, so multiple variety of module mounting structure will be available. So this is the closer view of that solar PV panel installation. So this is also an different view of solar PV panel installation. Okay, so I hope you remember I explained about the tilt angle. I will reiterate once again with respect to the ground plane like this. How inclined the module is. This angle is called as tilt angle. Okay, this angle is called as tilt angle. Okay, so the panel mostly we will install the panel in north and south orientation. So facing the installing the panel in a direction is called as panel orientation. Okay. So here the PV panels, all the PV panels will be connected in series as well as the parallel based on the requirement what I told to make the stringing, right? So the stringing is applicable for string inverter. Similarly, we have to perform the stringing for central inverter as well to match the nameplate detail of the central inverter. We have to do the stringing as well. Okay, so this is the photograph of the inverter room and the transformer and switchgear. In the right side, this is then inverter room IR. Okay, so in this inverter room, some locations the inverter will be placed inside the room as an indoor application. Some location inverter will be placed outdoor. So this is an indoor type inverter room. In this room, inverters will be placed here. So final outgoing from the solar PV panels will come to the inverter DC terminal, and inverter AC terminal will come to this transformer. This is an inverter duty transformer. So the inverter output terminal will come to this inverter duty transformer. So this inverter duty transformer output, most of the cases, it will be an 33 kV. So that output side, we will have an switch gear like this. Okay. So in this example, this is an inverter duty transformer. This is an inverter duty transformer. Inverters are here. So after the inverter duty transformer, there is a switch gear. This is a switch gear, 33 kV VCB. It has 33 kV VCB. So here, this is an switch gear. This is an outdoor type. They have provided one set also for that. So this inverter will, the inverter duty transformer output will go into this switch gear. So this after that it will go to the substation. Yes, yes. Okay. So some of the thing I would like to inform you. So in this photo, the switchgear are installed in a elevated platform. Here you can able to see there is an platform, right? So this is called as an elevated platform, and this is an inverter duty transformer. On that day, I told the inverter duty transformer, which having the oil capacity of 2000 liter and above, they shall have the uh, NFPA system, nitrogen based fire protection system. So this is an NFPA system control box. So it will monitor the winding as well as the oil temperature inside the inverter duty transformer. Okay, so this is an oil conservator. Then this is the inverter duty transformer cable termination. So as I told, this is an 5 winding inverter duty transformer. It having one HV winding and 4 LV winding. So this transformer having what you are seeing is the 4 LV winding. This is the winding 1, 2, 3, 4. So the inverter output is connected to this inverter duty transformer through this cable. So in this photo, what you are seeing right here, this is an cable. So this cable is used to connect this inverter duty transformer to the inverter. Okay. So in the opposite side, the medium voltage terminal will be there. So that is 33 kV. So from that terminal, it will go to the switch gear. Okay. This is an this is an NIPA system. And also there is one more thing called as fencing. Okay, so for all the transformer will be protected by means of fencing. So in order to avoid the unauthorized entry or unauthorized accessibility, so normally these transformers will be covered by fence and it will be locked. So who is the authorized person? They only allowed to access that. Okay, and also can able to see there is a distance between this inverter duty transformer to the switch gear. Okay, so this distance is called as clearing or clearance between the transformer. So this is a mandatory requirement for our India. So whenever there is an oil-based transformer, we should not keep other equipments very nearby. We have to maintain certain distance as an clearance. Suppose if we need to place two equipments very nearby due to land availability constraint, in that case we have to provide the firewall between the equipments. For an example, this is a switch gear, this is an inverter duty transformer. We have to maintain some space, let's say 6 meter. Suppose if we are not able to maintain this 6 meter distance, then what we have to do, we have to provide the firewall in between this. So this will be a firewall. This will be an switch gear. This will be an transformer. So in between, we have to provide the firewall. Okay. So this kind of firewalls will be required where space is not available in many of the inverter locations. So space will not be a constraint because the solar PV system is required so much amount of space. But in the substation within the city or substations, some substations where space is not available, those locations only firewall is required. Okay, so moving further, and this is an display of the inverter. As I already explained, this is the 2.25 MVA inverter. So this inverter having two modules. So both are equivalently rated. So this is the first one, and this is the second one. So combinedly, it is 2.25 MVA. Okay, and this is the switch gear, the closer view. So here you can able to see incomer 03 from IDT 10, IR 10. So what it means from the inverter room 10, the incoming feeder is coming like this. So here this is an IR10 inverter room 10. From here the cable is coming here. So there is an VCB here, VCB in this location. Then after that there will be an bus here. This will be a bus. So in this bus the outgoing feeder is here. Outgoing to, can able to see outgoing to PSS means power switching station. In simple words, we can say as a substation. So here they used the terminology that is power switching station. So it will go here. It will go to the substation. Okay. So this is the view of the substation. The backside, what you are seeing in the here is this is the power transformer. So in the power transformer 33 kV, it will get connected. One side it is the 33 kV, and these elements are outgoing is 230 kV. Let's consider 230 kV. So these equipments are yeah, 230 kV equipments. Okay, this is an CT current transformer. Uh, so there will be an switch gear for this also. Mostly high voltage application. Mostly we will use SF6 based switch gear. This is an SF6 based switch gear. Then from here you can able to see there is a transmission line. So here you can able to see this is the transmission line is going actually connected. So this power transformer output will be connected to this transmission line. So this line will get interconnected with the existing nearby substation. Okay. So now I came to the end of this presentation. That is ground mounted solar large scale solar PV system. I will summarize the presentation. In this presentation, I have explained about what is ground mounted solar PV system. And in ground mounted solar PV system, mostly we will use with the central inverters. And also I have shown the single line diagram. Then single line diagram with inverter duty transformer of 5 winding, and it having one HV winding of 12.5 MVA, and 4 number of LB winding of 3.125 MVA. So each LB winding will get connected to the one inverter of 3.125 MVA. So aggregated capacity, all the 4 inverters will become 12.5 MVA. Similar that is called as an inverter room. Okay. So in a plant, there will be a multiple inverter room. So the layout what I shown, in that there are 4 number of inverter room is there, and as well as one substation is there. Okay. So in the switch gear, we will have a BCB as well as the voltage transformer PT and current transformer CT. Okay. And also I explained about the bus PT and line PT. The PT installed in a bus called as bus PT, and the PT installed in the line is called as line PT. Okay. Also, I given some insight about the substation and about the collector network. So mostly the medium voltage network interconnecting the inverter room to the substation, normally called as connector network. Okay. Yeah, that's all from my end for this presentation. If you have any doubt, you can unmute yourself and ask your doubt. There is no doubt, we can wind up this session. I once again thank you for attending this lecture. I hope this will be more helpful to you. So if you have any doubts, you can reach out to me through email or WhatsApp. Thank you.